Hello everyone. Today, we would like to look at a differential equation problem. So let's begin. A chemical compound decays over time when exposed to air at a rate proportional to its concentration to the power of 3/2. At the same time, the compound is produced by another process. The differential equation for its instantaneous concentration is given as below, where N is the instantaneous concentration and the initial value is 2000. So what is the instantaneous concentration of the compound at 0.1 second? Let me look at Bashfort predictor character method to solve the differential equation. Bashfort predictor character method is a multi-step method where it needs more than one value of the dependent variable to compute the next value. It is also known as Bashfort-Moulton method. This method has two formulas. The first formula determines an approximate value of y, and it is known as predictor formula. The second formula is known as character formula. It improves the value of y obtained by the predictor formula. Note that the predictor formula is an explicit formula, whereas character formula is an implicit formula. To compute the value of yn plus 1, we need four values, which are yn minus 3, yn minus 2, yn minus 1, and yn are required. These values are called starting values. Note that the smallest value of n is 3, since the smallest starting value is y0. To find this value, generally any single-step method such as Euler or Runge-Kutta are used. To derive this equation, we have to consider a differential equation denoted as y prime with initial condition given by x0 and y0. Then, we integrate the differential equation between xi and xi plus 1 to find the value for yi plus 1. The second term of the equation cannot be determined as y is an unknown dependent variable. To find this integration, the function f is approximate by Newton backward interpolation formula. Thus, we can write the Newton backward interpolation formula as follows, where v equal to x minus xi over h, and f here is the y prime. Then, we can simplify the formula and substitute it into the integration. By solving the integration, we can have this equation. This equation or formula is known as Bashfort predictor formula. Then, we can use the same technique to find character formula. To find the character formula, the function f is approximate by the Newton backward interpolation polynomial. By using fi plus 1 and v equal to x minus xi plus 1 over h, we have the Newton backward interpolation polynomial as follows. Then, by this approximation, we can substitute it into the integration with range of x is -1 to 0. After solving this integration, we get this equation, and this is known as Moulton character formula. Then, this is the local truncation error for predictor and character formula. Now, let's try to solve the problem by using Bashfort predictor character method.
Firstly, we find the starting values using the fourth order Runge-Kutta method. This is because RK4 method gives the more precise solution with low truncation error. Initial condition given is n equals to 2000 when t equals to 0 second. So we find K1, K2, K3 and K4 and calculate N2. We get N2 equals to 1096.0214 when t is equals to 0.02 second. We repeat the same process for t equals to 0.04 and 0.06, and we get the answer for N3 and N4. Now that we got all four initial conditions, we substitute it in the ODE and get F1, F2, F3 and F4. Next, we use the Adams-Bashfort formula as the predictor to calculate N5. The predicted value for N5 is equals to 547.2215. Then we use the Adams-Moulton formula to correct the value. So N5 becomes 411.4993. We substitute N5 and T equals to 0.08 in the ODE to get the value of F5. Lastly, we repeat the predictor and corrector process to find N6. Hence, the concentration of the chemical compound is 451.7635 after decaying for 0.1 second.
Now let's look at some examples. This is January 2018 past year question. We can extract keywords like the ODE, age equals to 0.2, the interval 1 to 1.6, the predictor corrector formula, and the initial condition x0 equals to 1 and y0 equals to 0. Firstly, we find the starting values using the second order Taylor series formula. We differentiate the ODE and substitute it in formula, and we will get y1 equals to 0.24. Next step is to predict y2. Calculate f0, f1 and substitute it in the formula, and we will get y2 equals to 0.5761. Then correct it and obtain the value of y2. Do the corrector 2 more times as the question asks to perform 3 corrector iteration per step. So we will get y2 equals to 0.5983. Keep in mind to constantly update the values before doing the next step. Finally, we predict the value for y3 and correct it 3 times. We will get y3 equals to 1.2411 when the x is equals to 1.6.
Let's retry to solve another problem from January 2019 final paper. We have changed the original equation into this. So let's try to solve this by using Adam Bashfort predictor corrector method. Note that we can do only one predictor and many correction steps. In this example, we will use one predictor and 2 corrector. And we only have one starting value. Thus, we have to use other numerical method to find 3 more starting value. Therefore, we are using Rusyidah method to find y1, y2 and y3. We substitute the starting value into the given differential equation. Next, we find the predictor value and it is 3.0643. After that, by using this corrector formula, we can find the first and second corrector value. Hence, the final value for y1 is 3.2329. To make it more clear, it is better to create a conclusion by using table of t and y.
Let's look at one final example. This question asks us to use the Adams-Moulton method with h equals to 0.2 to find the value of y when x is equals to 0.8, given that the dy dx is equals to 1 plus y square, and initial condition is y0 equals to 0. Firstly, we find the starting values using the Rusyidah fourth order method, and we obtain y1 equals to 0.2027. We use the same procedure to obtain y2 and y3. Next, we use the Adams-Bashfort predictor formula to find the predicted value of y4 and substitute it in the ODE. Finally, we use the Adams-Moulton corrector method. We substitute the predicted value of y4 inside the formula and we will get the corrected value of y4, which is 1.0296. In conclusion, we can say that the Adams predictor and corrector method is very easy to understand and apply. It also gives a more accurate solution only by adding one additional function evaluation per step. However, we need to use another method to find the starting values and must be careful to update the values if there are more than one corrector involved. That is all from us about the Adams predictor and corrector method. Thank you very much.